In the systems I build, I use crystals in pairs that are counter-rotated to avoid beam displacement. Each of these crystals has a plus mark I have added for orientation. This plus mark not only shows you the orientation of the z-axis in the crystal, it also indicates the relative sign of the nonlinear coefficient. In this video, I want to show you how I test and orient these crystals. So I've got two cards down here as crystals. I've marked the direction of the z-axis in the crystals, and it's the angle that the beam makes with respect to the z-axis that determines the wavelength that will be produced by the crystal. Given that, you would imagine that since the rotating one of the crystals by 180 degrees leads to the same angle with respect to the z-axis, that you would have the same properties and conversion efficiency for the crystal pair. But what you find in practice is that 180 degree rotation leads to, for one side, one orientation to actually perform very well, and the other orientation to perform poorly. The reason for this is that a 180 degree rotation around the y-axis in these crystals is changing the sign of the nonlinear coefficient. This means that the relationship between the three waves that are being generated in the crystal are 180 degrees out of phase with what's being generated in the first crystal. In essence, the second crystal is actually in the wrong orientation, actually undoing what was generated in the first crystal along line center. So, to test the crystals that I get in, I use a crystal standard that I have that I've arbitrarily placed a plus sign on one side. I'll then take the crystals that I got in and put them in both configurations, and by either looking at the energy output from the system or looking at the beam profile output, I'll determine which configuration is correct, and I'll put a plus sign on it. Now, rotating that crystal by 180 degrees, I'd find the performance to be poor. I could add a minus sign at that point. Now, besides rotation around the y-axis in the crystal, if you flip the crystal over, the nonlinear coefficient changes signs as well, going, in this case, from a minus to a plus. Okay, this would be a proper orientation for the crystals, with the plus signs aligned. And it is the orientation that I like to use since the z-axis is oppositely oriented for the crystals, meaning that I need to counter-rotate them to maintain the same angle with respect to the z-axis. But this is the configuration that does not displace the beam. So the crystals, when you use them, since I just have a single plus marked on them, one plus on one crystal will be up and one plus will be down, and the two pluses will either be on the opposite or adjacent sides of the crystal. Now, I wanted to show you what I see in my test setup in the two different configurations. I'm working down at around 745 nanometers, so I was able to photograph it. And in the correct orientation, you'll see strong amplification along line center. And in the opposite orientation, you'll see almost a cancellation right along line center, with non-collinear phase matching in the O-wave plane compensating for the phase mismatch between the two crystals in the incorrect orientation. You can also make this determination simply by placing the second crystal in, for say, your OPO, and then trying it out in both directions. I use a power meter that I've placed at a distance away behind a small aperture that's centering centered on the central portion of the beam so that I could see a better change between the correct and incorrect positions. Turn up the energy here. And we can go into the program and rotate that second crystal and see what happens. Okay, that's in one direction. Let me stop. And I'll go flip the crystal around. I'll let it scan back through that position. You can see the second orientation performed a lot worse than the first orientation. So the first orientation was the actual correct one. Now there could be possibilities that you have a crystal that is multiple domain. In a multiple domain crystal, what is happening is the ferroelectric domains are inverting, causing like a plus and minus variation as you're going through the crystal. In those crystals, you're going to get poor conversion in either direction that you go through the crystal. So you need to look out for that. If you don't see a major difference in the two different orientations, then your crystal is likely multiple domain. Now you can do these tests with the OPA crystals, and it's actually a little bit easier to see what's going on. In the OP, I would put a power meter off at a distance behind an aperture centered on the beam axis, just like I did for the OPO case. I put the first crystal on with the correct orientation with respect to the z-axis that I want to use, and then add the second crystal onto OPA number 2, and then rotate it, looking through the phase matching at what I see is the energy output. And in the correct orientation, this is what I recently measured from OPA number 2. This is in the correct orientation, and this is what I see in the reverse orientation. Okay, so you can see there's a very dramatic difference on the output along line center for these OPA crystals. I would then go and add, after determining the correct orientation, add the next crystal in, OPA number 3, and rotate it. You can see in this configuration it looks like the poor configuration from OPA number 2. And in the correct orientation, you see a nice amplification. In the last crystal in the system, you even see a larger difference take place, where the wrong orientation undoes an awful lot of what the first 3 crystals actually did. But in the correct orientation, you get really nice amplification. Now, there is another way that you can look for domain structure in the crystals, and that is to send a weak 1 micron beam through the crystal and observe the green light that takes place. This green light is being made non-phase matched. It's being made by the last few hundred microns in the crystals, but it can tell you what's going on. I normally use the green that's created in the OPA crystals to tell me the direction that the 1 micron beam is going. For testing each of the crystals I get in, I stick them into a beam of about 100 to 200 millijoules and then look at the green light that's produced. If there is domain structure present, the interfaces between the domain boundaries have a greatly higher nonlinearity, and you'll see scattering, second harmonic scattering, away from the beam direction. And I wanted to be able to show that to you. I've got a block of 1 micron here, and I've got a crystal that I know is not single domain. It was made by a US company that thought they knew what they were doing. They are no longer in business. And you can see that besides the main spot from the beam, you'll see modeling and spots off to the sides. This is typical of what of the scattering that you'll see from a crystal that's multiple domain. Now I've got a crystal that's actually single domain in the OPA stage right now, so let me just block the beam, take out the bad crystal and see how it's performing. This is what I'm used to seeing from a single domain crystal. Okay, thank you.